Right, what we know so far. We've talked about Newton's gravitational law, which discusses the force between two masses, and that force is proportional to the product of the masses and inversely proportional to the separation squared. As I said before, if you double the distance between the two masses, it doesn't just halve the force, it makes it 4 times smaller, because 2r all squared is 4r squared, 4 times smaller. Remember, inversely proportional, so the force is divided by 4 times as much. Right, so we know that. We also know the definition of a gravitational field is the force per unit mass. And then G in terms of big G, if I replace F with this, G m over r squared divided by m, the little m's cancel to say that the gravitational field strength is minus G m over r squared. Okay, so that's what we know so far. So what I asked you to do today was to look into the gravitational potential and it's a little trickier, okay, to think about what this is, but hopefully when I've explained this it'll make a lot more sense. And even if it still doesn't make sense, try and follow the worked examples, and I'll do some more, so I'll make a couple more videos where I'll actually work through some exam style questions, and hopefully you'll be able to gain some insight into what gravitational potential is from watching me go through some questions. Anyway, what we need to do is we need to define this. Just like we defined the gravitational field as the force per unit mass, gravitational potential, and give that the symbol V. So you've come across this symbol before, electric potential, the voltage, how many volts you have. This is not in volts, okay? We will define it as the work done, and instead of the work done per unit charge, which is voltage, this is the work done per unit mass, okay? Given the units, work in joules and mass in kilograms. So your gravitational potential is measured in joules per kilogram. Okay, right, so that's the definition. Okay, in words you'd have to put out that it's the work done per unit mass, but there's a little bit more to it, and I'll show that in a diagram, and then hopefully you'll have this idea of what the very definition of a gravitational potential is. But it's linked to work. One thing, I've used capital W for work done, the amount of work needed. That's often a bit confusing because some people can go, oh, it's weight. That is not weight, that is work done. Okay. Right, so here is some planet, okay, and this planet has a gravitational field, because all mass has a gravitational field. And what we want to discuss is what the potential is, what the work per unit mass is, and we mean the work done moving it in the field, okay? So let's just say we want to get to point P. Now this is where it gets a little bit confusing, because you would often think about going from here up to P. However, that's not the best way of defining our potential, because of the fact that different planets, different sizes, different amount of mass, they'll all have different surface potentials. So what we can actually do is we can think about moving all the way out of the field, and I'll discuss in detail what I mean by out of the field, because you never really quite leave a gravitational field. The force, the gravitational force between two masses, acts over an infinite distance, so even at the far reaches of the universe there is still a slight attractive pull from a planet very far away to you, okay? but it's so small that you can kind of like start to say, well, that force is quite negligible. And so that concept then takes you to this point where you say if you can go an infinite distance away from the planet, you'll be in a zero potential. And this is where we define our potential to point P, not from going from the planet to point P, but going from an infinite distance away at zero potential, and how much work the field does to get you here. Okay? So at some point out, some infinite point, we're going to say that the potential is zero. Okay? And so the very definition now is the work done to move you, or your mass, or whatever the object is, often by definition you just say it's a small test mass, from an infinite distance at zero potential to point P in the field. Okay? And point P would be a certain distance away. And actually, in terms of R, we often say to the center of the planet. So distance R is all the way to the center. Okay, so we're going from an infinite point to point P, and it's the work that is done on that mass, and that's what we define as the potential. Okay, so that's where it gets a bit tricky, because it's kind of counterintuitive that you would go from nothing to that point. Everything really says, well, why don't we start at the planet and see how much energy is required? What we're talking there is the amount of energy you put in to raise your gravitational potential. Okay, rather than going from an infinite point and the field doing the work to get you there, because any mass in this field is going to have work done to it by the field to move you to that point. Right, so that's the definition. Okay, so that's the equation out of it, but the definition is the potential at a point P in the field is the work done on the object, so on whatever mass you have, to move from an infinite distance to point P. Okay, right, so that then means that everything then from infinity towards the planet is actually a negative potential, and that should make sense because of this negative value that describes an attractive force. So we have a negative value here, and we can actually define V in terms of G. I'll spend a separate video doing that. Okay, what we're actually going to do is we're going to integrate that force over a certain distance, because if you integrate a force distance graph, you're going to get the work done. Okay, just briefly going back to the energy topic. If you apply a force and you move something it's displaced a certain distance, depending on how that force is applied. Is it a constant force? Is it a linear force? Is it increasing but a linear amount, or is it some sort of varying force? However you work that out, going from one distance to another, you would work out the area under. Okay, so you're actually integrating to find that. So that's going to be a separate video to work out the link between your potential and the force required. Okay, but to make it simplified for this video, just so that you get the equation for V in terms of G, what you can say is, if you do have the starting point, which is the work done per unit mass, but you know that work done is force times the distance moved, and the force from Newton's law is minus G m, okay, over r squared. If you cancel those r's and you cancel those m's, you end up getting V as minus G times the mass of the planet divided by how far away from the center of the planet you are. So you can work out any gravitational potential in that field depending on the planet and how far away you are. So I can use this with an example to work out the gravitational potential at the surface of the Earth. Okay, so if I have, there's the Earth, and I want to know what the potential is at this point. I would just do G times the mass of the Earth, and I would divide that by the radius of the Earth, because obviously at the surface you just, from the centre, just the radius of the planet. So let's use some numbers. Let's say that we know G is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And the mass of the Earth is 6 times 10 to the 24 kilograms. And the radius of the Earth is 6.4 times 10 to the 6 meters. So if I put all these numbers into this equation, so we do 6.67 times 10 to the minus 11 multiplied by 6 times 10 to the 24 divided by 6.4 times 10 to the 6, and remember it's a negative number. That then comes out as approximately minus 6.3 times 10 to the 7 joules per kilogram. So that is the potential at the surface of the planet. And we can do a number of things with this. We can actually work out how much energy would require to totally escape that field, to go to that infinite distance. And that would lead us on to working out potentially how fast we'd need to be going. And so we can work out the escape velocity of an object needed to escape a planet. I'll do that in a separate video. Or alternatively, we could actually say how much energy is required to go to certain positions in the field. So for instance, a good example is to say if I have a certain amount of mass I want to put on the International Space Station, which is a certain distance away, a certain height above the Earth, we can work out how much energy would be required. And I'll do that in a separate video. Okay, but for now, I'll leave it here. So what we've done, what we've talked about, is that your gravitational potential is the, by definition, the work done on a unit mass to move it from an infinite distance at zero potential to a certain position, a certain distance away from the centre of whatever planet that's gravitational field you're in. And then it's in joules per kilogram, and it is, something I didn't say, it's a scalar quantity. It's linked with obviously energy and mass as scalars, and it's a negative value. It becomes more negative the closer to the planet you get. Okay, and you can think about putting energy in to actually escape the planet's surface. So if you want to raise your mass up, you need to go a certain distance, you need to put in a certain amount of energy. Okay, and so you can think about, even though energy is a scalar quantity, putting energy in, okay, you say you're adding energy, that's a positive amount. If you lose energy, you can say that's a negative amount. So to raise your gravitational potential energy, you need to put energy in, okay, and then you'll be at a less negative potential because you'll have gained gravitational potential energy. In fact, one more thing, just to tie this nicely in. If I do say that the potential is the work done per unit mass, you can work out the work done by doing mass times the potential, but it's not just the potential. Usually going from one potential to another, so you're working out a change in potential, and this is what's your potential difference. Okay, so the work required to move a mass through a potential difference, okay, that can be calculated, because you can calculate the potential at any point by using this equation. So what I'll do is I'll leave it here, and then we'll use these equations in a worked example, okay, and that'll hopefully explain a lot more. But yeah, I'll leave it there.